speak about the joint work with Andrei Negut from MIT. And Jake Rasmussen from Cambridge University. And the main problem that we'll study is the following basic question. How to compute Kavanagh homology and Kavanagh-Rosansky homology of torus nodes. And some other big classes of nodes, but torus nodes are arguably the simplest possible class of nodes, and a lot is known about them, but still it's not known how to compute their Kavanagh homology. And I will not define Kavanagh homology, so I'll rely on Alexander's nice exposition on Monday, and if you miss his talk, then this is some black box, but this is very important topological invariance of nodes, but again, it's very unfortunate that we don't know the answer for torus nodes. So what do we actually know? So first of all, we know, so Kavanagh homology is a generalization of John's polynomial, so we certainly know John's polynomial. And we know Homology polynomial. And this is due to John's in his 87, I think, paper. So there are very explicit formulas, some sums of rational functions, which allow you to compute John's and Homology polynomial of torus nodes. And also there is a lot of experimental data for Kavanagh homology. So there are a lot of programs, and mainly due to Alexander and Barnatan and some other people. So if you want to compute homology of any given torus node, like, I don't know, 8, 9 torus node is still okay, you can plug into the program and you'll get some huge polynomial which tells you what are exactly the groups in this homology, but so far there was no obvious pattern in this data, and that's the problem that we addressed. And also for Kavanagh-Rosansky homology, the definition is much harder, so there are not so many programs, but there are still some computations for small torus nodes. So for Kavanagh-Rosansky, some computations for small nodes. Up to 6 crossings, 7 crossings, or something like this, but that's really small, and for torus nodes it doesn't explain anything. And until, I would say, last year, this was the state of the art. So we knew John's polynomial, we knew that Kavanagh homology was much bigger, and there were several conjectures describing this homology, but what we had only this experimental data. Last year there was a very nice breakthrough. So the first result that I'd like to mention is about the limit as m goes to infinity of torus nodes and m, which I will denote by t and infinity. So of course there is no such node, but there is a well-defined stabilization procedure, and you can check that if you know the formula for Homology polynomial, it will stabilize. So let me say that John's polynomial stabilizes to Sn colored a knot. So John's polynomial a knot, which is known, which is very easy to describe, and also Homology polynomial converges to Sn-colored Homology polynomial of the unknown, which is again given by some very simple formula. And so a theorem of many people due to Stoschich. Huh? So it converges to some series, but this will be very least rational function, and this will be like some numerator and denominator. If you expand it, that will be the limit of this polynomial. And strictly speaking, there are again two limits because there is a head and there is a tail, so you can choose where to normalize. But let's say one of them converges to symmetric colors, another to antisymmetric colors. Both of them are very easy. So theorem of Stoschich, Rosansky, in different contexts by Kautis. So there exists a limit and goes to infinity of both Kavanov and Kavanov-Rosansky homology. And in some precise sense, this can be thought as a Sn-colored homology of the unknown. So this is another interesting question, but of course it's much more complicated than this. But surprisingly, very recent theorem of Hogenkamp last year says that the limit, so Holm-Fly homology, of T and infinity can be described as following. So this is a polynomial algebra, so let me say with Q coefficients and even variables, and also tensor exterior algebra and odd variables. Let's see. So this is Homology homology. It's homology theory whose only characteristic is Homology polynomial. It's a version of Kavanov-Rosansky homology. And the answer is very clear and very nice. So this is just a free polynomial algebra in n even and n odd variables. And this is by no means obvious because if you remember the definition of Kavanov homology from Monday, then you have to take a node, you have to resolve all the crossings, do some complicated algebraic procedures, and the bigger the torus node is, the bigger the answer should be. So there is no obvious way to see this, but rather you use some tricks. So you resolve some of the crossing, and then you use some Reidemeister move, and then you use some other crossings, and so on. So this is a tricky thing, but the proof is not so complicated in the end, but this is, nobody somehow thought about this before. And one way to think about this philosophically, at least as I think about it, is that torus nodes are in some sense similar to Grassmannian. So if you think about homology of finite Grassmannian, it's complicated, but if you go to the limit, you get free polynomial algebra, just as here. So there is some similarity. Of course, it's some bit artificial, but it's how it looks like. Okay, so what about Kavanov homology in this limit? So let me mention some conjectures and theorems. So there is a theorem of Rasmussen which says that there is a spectral sequence which starts from Homology homology, so E, let's say 2-page Homology homology, and E infinity page will be Kavanov homology. So for any node there is such a spectral sequence. Sometimes it's possible to compute it, most of the time it's hard to compute it. But in this limited case we had a conjecture how to describe it. There's a difference in spectral sequence to non-Floer homology, yes, but it's kind of unrelated. So for every n, there is SLN Kavan-Rosansky homology, and there is a spectral sequence corresponding to that. So in this case, we're lucky because we know Homology homology, so the conjecture, you and myself, along with Rasmussen and Shendy, says that there is only one non-trivial, so for this limiting torus knot, there is only one non-trivial differential, and namely the differential of xi is 0 and the differential of psi I is something like sum over all j from 0 to I x j x I. So this is also fairly easy, but the surprising thing is that the homology of this differential are very complicated. So we compute this homology and we have some numerical data. So this agrees with numerical data up to n is equal to, so this is checked up to n is equal to 8, because n is equal to 8 is really the limit when this Barnatan's program works. And the answer is very complicated, and the answer, so the Poincare-Poincare series, is related to the so-called Rogers-Ramanujan identity, which was mentioned earlier. And also, you can define all these things over z, in fact. So you can put z coefficients here. And then here you say, okay, all coefficients are 1 or maybe 2, but in fact you have tons of torsion and you can recover all the torsion that people saw, especially again Alexander, in Kavanagh homology a long time before. So you have torsion of all possible orders even with this simple differential. But this is still a conjecture. Right, and another positive result that is known is again due to Hogenkamp, so maybe I'll mention it here. So another result is the theorem Hogenkamp. Was. So they computed, so let me just not write the formula, but say that they have explicit description of, again, Homology homology of n torus knot. So this was very explicit, and this was more complicated, but still they have some explicit recursion in n, and they have some computer program which computes it, and they actually prove that this is true for all n, again by some clever tricks with Rider-Master moves and resolving crossings and all these things. So there is some explicit recursion. And in principle, it seems that their method can be adapted to many other torus knots, but somehow the question is how to pack all this information in some way that will be more understandable. And that's what I'm going to talk about. Okay, so I'd like to formulate a long conjecture, which has many, many different parts. But stay with me. So this is, okay, so the first part is that we define an algebraic variety which I will denote by FHN. And FHN stands for the Hilbert scheme. And I will say later what the Hilbert scheme of what and what it means to have it to be a Hilbert scheme, but this is really complicated, not really, but this is quite subtle algebraic variety. But it can be described very explicitly. And then on this algebraic variety, we have the following structures. So first of all, there is a rank n bundle, vector bundle, T on FHN, which is some sort of tautological bundle. And the main conjecture is that for any braid beta on n strands, there exists a, well, another bundle or strictly speaking a sheaf or complex of sheaves, but let's not go there. Let's say that there exists some vector bundle, maybe line bundle in many cases, which are interesting, which I will denote by I lower star of beta, such that the Homology homology right up here, so the homology of the closure of beta will be in fact the space of sections of the following thing. So you take this I lower star of beta, whatever it is, and tensor with exterior algebra of T dual by some reason. So I'm sorry for this mess of notation. But anyway, so there is a fixed vector bundle. You take the exterior algebra of the dual. So this will be huge vector bundle. You tensor it with I lower star of beta, which I didn't explain at all. Compute the space of sections, and if you're lucky, then this is conflict homology of beta. And again, if you want to be precise, you have to replace the space of sections by a sheaf homology. And I don't want to see anything here, so in fact it will be sheaf homology. Oh, because I can write I lower star of beta very explicitly in many cases. So I'll show you an example in a second. So in many cases, the advantage is that I can compute I lower star of beta, and I will describe it. And in some sense, we have a general method, but this is not so direct. In many cases, we have direct description of I lower star of beta. And then we can use algebraic geometry to compute the space of sections. So for example, we can use ideal-Bott localization to fixed points and many different things. So I'll say something about it later. But right, so space of sections is fine. So now the next thing which actually makes this a bit more interesting is what are the properties of I lower star of beta. The properties are that there is a family, there is a commuting family of braids which can be drawn as follows. So you take a strand, take something like this. So let's say this is K strand, and this will be denoted by LK. So these are sometimes called Jucys Murphy elements, sometimes called some generalized Jucys Murphy elements, but they're well known in skein theory, in representation theory of Hecke algebras. So these are some versions of Jucys braids, and the key property is that they commute. So LK LM is equal to LM LK, because, for example, if M is bigger than K, then it goes around, but it doesn't interact with this braid. So they actually commute in the braid group. And another property is that, for example, L, if you take the product of all these things, and this will be a full twist, or this is N torus braid. And so we have this nice family, and we want to require that this nice family behaves nicely with respect to I lower star, whatever it is. And so we require that I lower star of beta times LK is the same as I lower star of LK times beta, and is the same as I lower star beta tensor with, let's say, curly LK, where this is some line bundle on the chin. So if I know the shift for beta, I know the shift for, or if I know the bundle for beta, I know the bundle for beta times LK. And for example, if I know that I star of 1 is the trivial bundle, then I know that I lower star product of any LK in any power AK will be just the product of these line bundles in the same power AK. And this is very explicit. So if I know any braid which is obtained by composing this Jucys Murphy element, then we have some line bundle on this log Hilbert scheme. So there are some other versions where we can apply exactly the same argument. And so this is fortunately not the end of the conjecture. So there are two more things. So one thing is about the gradings. So you may ask, what about the gradings? So on Holmes-like homology, I didn't say what it is, but you know that in the Holmes-like polynomial there are two variables, Q and A. So Q is equivariant grading. So Q is equivariant. And A is the exterior degree in here. And there is another gradient, which is homological gradient, and which in this isomorphism becomes another equivariant gradient. And what I mean by equivariant, so there is a natural action. So there is an action of C star cross C star acts here on FHN, and there are two equivariant gradients on the space of sections. So if I lower star of beta is equivariant under the section, this is equivariant, and on the space of sections, we have action of C star cross C star, and these are two gradients corresponding to this. So this is it. And the last thing which I want to mention, I shouldn't, but anyway, so the last thing is that this Rasmussen spectral sequence is induced by some section of T. So if you have a section of T, you have a map from lambda I T star to lambda I minus 1 of T star. And so this gives a differential on the standard product. And the corresponding spectral sequence will be conjectured the same as Rasmussen spectral sequence. So in particular, if we apply all this, we get not only the form free homology, but all SLN homology in some not so direct way. Okay, so this is this very long conjecture, and again, it would be very nice if it, yes?
Sorry. So, for instance, in this case, you know how to construct this? That you conjecture its inequality, or you conjecture the existence and you don't know how to?
We know how to construct the conjecture of equality, let's say, yes.
And then can you prove that the right-hand side is invariant by Markov rule?
Yes. 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 So we certainly have some geometric version of Markov rules. So there are some substances, but not there. So I just want to say that this lower star is certainly not invariant because it depends on n. It depends on the number of strands. But there is some version, some geometric way to relate this FHN to FHN plus 1, which corresponds to Markov rule. And that's good. All right. So this is very nice, but not so clear. So let me give you some examples and see. Huh? No, in this case it's not about algebraic. No, here algebraic nodes are not so natural. So what is natural is really you start from some, let's say, torus node, and you add some twists with corresponding to this LKs. So you can think of this as you take some number of full twists on n strands, some number of full twists on n minus 1 strands, and minus 2 strands, and so on. And this sometimes it's called twisted torus nodes, and that's the natural family here, because somehow we want to stick with this aligned LK. And algebraic nodes are harder. All right, so examples. So for n is equal to 2, there are not so many things. Let me actually define this FHN. It's not so hard. So this is the space of pairs of matrices such that X is lower triangle Y is triple lower triangle. And then X and Y commute, and up to conjugation by triangle matrix. So I'm lying a little bit, so there is some other stability condition here, which I don't want to mention, but essentially this is just last, let's say, stability condition. Huh? And n by n matrices. And I don't want to say what stability condition is, but essentially this is just a set of pairs of commuting matrices after conjugation, but we require them to be triangular. So example, let's say for n is equal to 2, we have x, which is x1, x2, 0, z, and y, 0, 0, 0, w. So the commutation relation says that I have 0, 0, 0, and here w times x1 minus x2. So this is my equation. W times x1 minus x2 is equal to 0. And then you can check that after conjugation you have two choices. So one choice is that x1 is not equal to x2. Then w is equal to 0. And then we can make z to be 1 by conjugation. Again, z is not 0 because this, by some reason. And so the matrix will be, so the only parameters that we have are x1 and x2. So we have C2. And if x1 is equal to x2, then w could be anything, but the ratio of z and w is fixed, because if I conjugate, I multiply them by the same number. So in fact, I will get CP1 with coordinate. And so my space would look like the following. So you have CP1, and then you have a line, C, and then all these things, let's say 10 times C. So I have 2 points which are either different, and then I have C times C, or I have 2 collider points, that's the C plus an extra coordinate in CP1. So that's strange algebraic variety, but it's somehow nice. And then, so the answer, so that's really easy to check. So what do we want? We want some bundle on this thing, and I just want, so let's say this is S. So if I have S in even power, then this will be line bundle of K on, let's say, and this, if I have S in power 2K plus 1, this will be O of K on CP1 cross C. So this is, if I have O of K on CP1 cross C and I have nothing there, then this is, well, not a vector bundle, but this is well-defined sheaf, and that's what we'll need. And so it's an easy exercise to compute the space of sections, and an easy theorem, let's say, proposition, is that the conjecture is true. For n is equal to 2. So basically, I just gave you the answer. Again, I didn't say how I guessed it, but this is very natural. And also, S squared is L2. So this is this thing. And this is just L2. And so we check that L2 corresponds to tensor with O of 1 on this thing. It's a bit more complicated, but I mean, it's not so hard, yes. In this case, everything is not so hard. You can compute it by definition. One interesting thing is that if you have odd keys, so you get a node, and so homology is, at least reduced homology is finite dimension. And that's what you see, because here you have compact space. And if you have a link, reduced homology is always infinite dimension. So it grows like the number of components, more or less. And here you see that it's worked on this thing, so it's infinite. So a more interesting example is for n is equal to 3. So I don't want to do a complete description. So FH3, in fact, has 5 different components. So here we have 2 components, and there will be 5. I don't want to describe all of them, but one of them is a cubic Hirzebruch surface. is the projectivization of O plus O minus 3 over P1. So you take this rank 2 bundle over P1, take projectivization, you'll get P1 bundle. So this is CP1 bundle over CP1. And on this thing, you have a lot of interesting line bundles. And again, you can describe explicitly the space of sections. So algebraic geometry tells you what it is. And so we know in particular all homology of torus nodes in this way, and this is very explicit computation. So let me just leave this. And now what is the main idea of construction? So, and how it's related to quantum topology after all. So the idea is what is called categorical diagonalization. Okay. And I don't want to explain much about it, I just want to recall the classical fact. So the classical fact is that so we have this guy's LQ. So we can project them from the Bray group to the Cake algebra. And the fact is that because all these operators commute, so LK diagonalize simultaneously so the eigenvectors correspond to irreducible representations of Higgs algebra. So let me say this. So we know that this is a Q deformation of the group algebra of symmetric groups. In particular, it is direct sum M lambda, where lambda is a Young diagram of size n, and V lambda is an irreducible representation of Hn. And M lambda with some multiplicity. M lambda is in fact the number of standard Young tableau of shape lambda. And so the LK diagonalize simultaneously, and the eigenvectors are projectors to irreducible representations. And so there are as many projectors as standard Young tableau. So standard Young tableau is the way to fill Young diagram with numbers. So they increase this way and this way. And so the eigenvalues are the following. So you have this tableau, so let me draw an example. So eigenvalues are Q in power contents of boxes. In lambda. So here, the content of box is the difference between x coordinate and y coordinate. And so here, the content will be 0, 1, 2, 3, minus 1, 0. And so the eigenvalues of Lk will be, again, so L1 by 1, L2, with look where 2 is, and the eigenvalue will be Q, L3 will be Q squared, L4 will be Q in power minus 1, and L5 Q cubed, and L6 1 again. So for every Young diagram, we can compute all these eigenvalues and eigenvectors. And now what is the kind of decategorified version of this I lower star? So I lower star is, in fact, the categorification, in some sense, of the projection of the full Hecke algebra to the commutative subalgebra generated by Lk. So we have a family of commuting operators. We can generate a commutative subalgebra in Hn. And there is certain non-degenerate pairing in Hn. We just project into this subalgebra. And if we know all these eigenvectors and eigenvalues, we can do this very explicitly. And the construction of a lower star that we see is that we use some kind of categorification of this construction, and I certainly don't want to go into any details. I just want to mention recent result, again, Logan-Camp and Elias. So, another theorem. Elias is that in the context of Fontley homology, I don't want to see what it means. This Lk diagonalized in the categorified Hecke algebra, again whatever it is, and the eigenvalues are q in power x, t in power y. So here we say that it will be q in power x minus y, and in this categorified version there will be just q in power x and t in power y. And we use this construction to connect it to geometry. So let me say, in the last 5 minutes, let me say how it's related to geometry. And actually, before geometry, so in this limit, when we go to large torus node, what happens is that we just take an operator and apply it many, many times. So the result will converge to the eigenvector with the highest eigenvalue, lowest eigenvalue. And this is precisely the projector to the symmetric representation that we see. And here again, it will be some version of this. So how to see all this diagonalization in geometry? Well, we have, so let's suppose that we have some variety, for example, of Hn, and we have this line bundle L. So what are the eigenvectors and eigenvalues? So, and let's say we have some covariant action C star. So one possible definition of eigenvector and eigenvalue, again, there are some categorical versions, but naively you would say that eigenvectors are just fixed points of this direction. And the eigenvalues are the weights of L at this point. Because at this point, okay, what happens is that L, if you want to, the skyscraper shift at this point gets multiplied by L. It will become the same thing times the weight of L with respect to C star at this point. And so there is one-to-one correspondence between eigenvectors and fixed points, and we can check that there are as many fixed points of torus sections as standard tableau. The weights are exactly the same as predicted by this. And in particular, so in our example, if we have this T and infinity, so this corresponds to fixed points with highest, in some sense, eigenvalue. And the homology is like the local ring. So, homology. Like the local ring. Of region. At that point. And so the reason why the homology is a free polynomial algebra is because this algebraic variety is smooth at this point, and so this is just a free polynomial algebra. And if you take any other projector or consecutified projector, the algebraic variety will be no longer smooth, and homology will have interesting structure, and this is again predicted by this conjecture. And I think I would stop here.